Hello, this is Dr. Wood with Citadel Civil Engineering. This is CIVL202 Statics, and in this lecture we're going to be breaking down a two-dimensional vector into its components in a Cartesian coordinate system. So to start with, we have our vector here. It has magnitude and direction, as vectors do, and we need to place it on a Cartesian coordinate system. Cartesian coordinate systems in 2D hopefully are familiar to you. They consist of a vertical y-axis and a horizontal x-axis as shown. These two axes should be orthogonal, 90 degrees from one another. And what we're trying to do is find out what components along the x-axis and along the y-axis we could add together to get this vector A. Down here, we're going to have an angle that we could label theta A, like so. And this is where we want to start. Now, if you want to, it might be helpful to you to have some physical models with you. So if you have some connects, you might be helped by building yourself a little vector here, okay? A little vector like this. For the moment, we're going to ignore these white sticks, although they do indicate the x and y systems. And then maybe making yourself a sheet of paper that shows the x and y with some scales on it. So the idea here is that we might be able to take this little vector here and we would put it on our x and y scale like so. So it's over there in quadrant 1. And then what we want to do is we want to project or cast a shadow from the tip of the vector down to the x-axis. And so a way we might model that mentally is if we lay this down horizontally and we put this guy here, we might use a light source like our cell phone to shine a light and cast a shadow that would run vertically down to the x-axis, and then do the same thing on the y-axis. Let's look at what that would look like up here. So if I put my light source up here and it casts a shadow down, I would be able to project a line down to there. And likewise, I could put a light source here and project or cast a shadow, project back onto the y-axis. And that's going to give me a new vector, one here called AX. That's the projection of A along the x-axis. And one here called AY, which is the projection of A onto the y-axis. And hopefully when you look at this, you'll notice something. What have I drawn? I've drawn a parallelogram. And it turns out that we have our parallelogram law that let us add vectors. We can also use it to resolve vectors into their components. Now, as I recall, we didn't actually like the parallelogram law all that much because it involved drawing parallelograms and these different things, but the triangle rule might be more helpful. And so I could draw the y component just as easily over here. It has the same magnitude and direction. And now I'm looking at a right triangle. And so what special functions do we have that relate the lengths of sides of right triangles? Hopefully, sine, cosine, and tangent immediately come to mind. And so if we remember our SOHCAHTOA, maybe you learned a different mnemonic device to remember it, but the sine of some angle is going to be equal to the opposite side divided by the hypotenuse. The cosine of some angle is equal to the adjacent side divided by the hypotenuse. And the tangent of some angle would be the opposite over adjacent. Hopefully this looks familiar to you. All right, now when we look at this triangle here that we've drawn with the angle theta A, so let's make these all theta A's, we'll now notice some components about the magnitude. So one thing we'll notice here is that AY represents the opposite angle. And so we can say the magnitude of the y component divided by the overall magnitude is equal to the sine. And that would let us solve for the y projection. AX is adjacent. We know it's adjacent because our angle line touches that x-axis, which means that our cosine can be resolved as AX over A. And then tangent would let us relate AX and AY directly. Now, what we'll find is that if we use our sine, cosines, and tangents, we can always break these things into their components. And what that indicates to us is that if we add ax to ay, we'll get vector A. And we can see that tail to head, we get the total vector. So that's what we've got going on for us there. Another question we might have is, so if we want to take this and we want to break it down, we're going to follow a procedure. So this is the procedure you might write for some of your homework problems that deal with this. The first step is going to be to draw our picture. Remember, our homework format requires us to draw a picture anyway, so we're going to want to sketch the triangle. And then from the triangle, we'll want to use trig, sine, cosine, tangent, to ID our components. And then we can solve for our final vectors or write our vectors. And so what we've done here is we've drawn our triangle, and now we can use trig to solve for this. So if we're trying to break this into pieces, we might know theta A and the overall magnitude, and then we can use that information to solve for our unknown components. So in this case, I've actually written 3 equations, and I only have 2 unknowns to solve for, because the tangent in this particular case might not be the most helpful. So I can then rearrange these equations and I can solve them, and that would be great. There's one more relationship we might use for a right triangle, and hopefully what's coming to mind to you is the Pythagorean theorem. And the Pythagorean theorem tells us that the magnitude of the hypotenuse squared is going to be the sum of the squares of the other 2 sides. Like so, Pythagorean theorem, or maybe you prefer to put the square root in there, like so. And this is going to give us the overall magnitude of A. So at this point, we're analyzing our system. Now, to resolve or to write the vector, we need some notations. Now, the first notation we might use is scalar notation. And we'll remember that vectors, unlike scalars, so a vector has its magnitude and components, but the scalar, or magnitude and direction, scalar only tells us about the magnitude. And so in scalar notation, what we will typically do is we'll write the magnitude and then draw an arrow to indicate the direction. So we've actually already done this before, but we could say A is going to be equal to the magnitude at A at the angle theta A up from the x-axis, like so. And this would be scalar notation. We've done this before. But if we wanted to write its components, we would say that A is going to be equal to AX along the x-axis, so we're going to need an arrow there, and AY along the y-axis. And so magnitude arrow, in this case what we're going to do is take a look at AX. We would use, in the way we've got this theta A described, we'd use the cosine. And so we'd multiply the A across and we'd be able to say A cosine theta A. That's my magnitude. And then I'm going to give it the direction arrow. And I've drawn a little positive sign, so now it makes a plus with an arrow to the right. And that indicates my positive direction there. Likewise, I can use sine to solve for AY in this case. And then that's going to give me the vertical component. So this is scalar notation for this same thing. Now, I want to draw one important thing to your attention. Some of you might have been taught in your math class that when we have our angle from the x-axis, that we can always use cosine to find the x component and sine to find the y component. And that is true when our angle is drawn positive from the x-axis. But what would happen if instead of giving you theta A, I gave you this angle, phi A? Well, now we could do the other side of the triangle, yes? And we would have AX, now looking at the top component. But what you'll see is that AX is now the opposite component. So sine would give me the AX. And cosine is now the adjacent, or AY is now the adjacent component. So cosine would give me AY. And what I'm trying to draw your attention to is that you've been taught a particular way in mathematics, where as long as your theta A is defined to the x-axis, you can always use sine or cosine. But what I'm trying to get you to do is build a better mental model that says that when I approach a problem like this, regardless of which way the coordinates are pointed and which angle is given to me, I'm going to sketch an acute triangle. So I want an angle less than 90 here. And then from there, right triangle, I can use my sine and cosine, where my angle indicates opposite, or in the case of phi A, opposite, which I'd use my sine for, and my adjacent, where the angle touches, I'd use cosine. There's one more tool that we might use to do this, and it's called a similar triangle. And hopefully, again, this is review, but sometimes we'll see instead of an angle, we'll get a little triangle here where the lengths are known. Typically, this is a 3, 4, 5 triangle, but it can be other things. And so we might have some base, some height, and some length. And what we're going to notice is that this little triangle, this slope triangle, is the same ratios as the big triangle. And so we can come out here and say, well, my AY, that's my vertical component, matches my vertical component of my smaller triangle over the length. And so I can get this ratio H over L, where if I'm using similar triangles, I would know both of these terms. And then I can solve for AY. So I just do A times H divided by L. Or over here, AX, well, X is horizontal and B is horizontal. So B over the length matches the same direction as the area. And so again, I can, given those, solve for AX. Or even if I had the tangent, you'd say H parallel to AY divided by B parallel to AX. And again, I have another ratio I can use to solve for my potential unknowns. So similar triangles. So already we've talked about sines, cosines, tangents, similar triangles, and the Pythagorean theorem to build out our scalar notation. So this is to identify our components. Now the last way that we might express this in 2D is to go from scalar notation to Cartesian vector notation. So Cartesian vector notation, which can be summarized or abbreviated as CVN as opposed to scalar notation that might be SN. And to use Cartesian vector notation, I'm going to introduce the idea of a unit vector. And a unit vector is a vector whose magnitude is 1. So it's going to have a magnitude of 1 and then tell me something about the direction. So a vector with magnitude equal to 1 that gives me just direction. And the way that we indicate unit vectors is by giving them a little hat, not an arrow, but a little hat. And in Cartesian vector notation, we have in 2D 2 unit vectors. So one of them is I. You can see how I've given it a little hat there. And the other one is J. And again, instead of a dot, I've given it a little hat. And if I want to relate that back to my scalar notation, I is going to have a magnitude of 1 going in the positive x direction. We might even label it that way with a little x out there indicating my reference line. And J is going to have a magnitude of 1 pointed in the positive y direction. And so when I looked at my little Kinex model here, I had these little white vectors, and we can think of them as being unit vectors. So there's my j vector and my y unit vector. Each one in my scale is 1 long, right? You can see that. It's a little hard to tell with the perspective on the camera, but hopefully that gets the idea if you build that model for yourself. And so this can be super helpful to us because now instead of having to draw arrows and have brackets and kind of weird things to deal with that, we instead can use the notation of addition with our i's and j's to capture the direction components. So if I want to talk about the magnitude of the magnitude and direction, vector A, in Cartesian vector notation, I'm going to say that's going to be equal to AX in the I direction plus AY in the J direction. And so we see where we have the magnitude and the unit vector that tells me just direction. So this is AX horizontal, AY vertical, and it's addition. So if I go from AX to AY, I'll find the overall vector A. I could then, of course, use my Pythagorean theorem to find the overall magnitude if I knew its components. Or I could use sines and cosines to write this in, more verbose form, where we would say that A cosine theta A in the I plus A sine theta A in the J is equal to my vector A. And I've got a little line wrapping going on here. All right, so that is breaking our vector into its components. We've projected to AX and AY. We've drawn our triangle. We've used our trig, either sine, cosine, tangents, or similar triangles to identify equations that will tell me my components. We can talk about it in scalar notation with arrows indicating direction, or Cartesian vector notation with i's and j's indicating direction along the x and y axes. In our next lecture, we'll look at the addition of vectors using the vector components in the Cartesian coordinate system. Thank you, and I'll look forward to seeing you then.